maximum likelihood estimator? Strictly speaking, the maximum likelihood estimator is given by this. What this represents, it represents the likelihood of observing your data set where your data is labeled x1 through xn and the observations are assumed to be independent. Um, this likelihood function, it says multiply the density functions evaluated at the observation xi for every data point. And this represents the likelihood of observing each and every one of your data points. In practice, we want to estimate an unknown parameter with this likelihood. That's given by this theta here. So what value of theta maximizes the likelihood of observing your data? And the key word there is optimize or maximize the likelihood. So if we're maximizing the likelihood, oftentimes we're taking the derivative. And something that makes our life a lot easier is to take the derivative of the log of the likelihood. This gives us the same critical point as the original likelihood function, and you can prove that. Okay. Um, so let's run this uh, this graph and look at what the maximum likelihood function does. Okay, so here we have data that's generated from a normal distribution, but don't know we don't know the mean of the distribution. Okay, and so we want to estimate the mean of the normal distribution. What we have here is we have two blue normal distributions placed at 4 and at 6. So the question is, why not choose one of the blue distributions? Well, the blue distribution, it's not the most consistent with the data here on the x-axis, the sample data. The distribution that makes it most likely to observe this data set where it's on the x-axis is this red curve, and that's the maximum likelihood estimate. Now, the unknown parameter is the mean, which is the peak of this distribution, and the thing that makes it the most likely is when it's equal to the sample average, which is this dashed line. Now, you might ask, why isn't, for example, this leftmost blue curve the maximum likelihood estimate? Well, it wouldn't be very likely to observe this data on the far right between 6 and 7, whereas it would be much more likely under the red curve. Okay. Now, conversely, for the the blue curve on the far right, it wouldn't be very likely to observe these 2 points on the far left close to 3, but it would under the red curve. So this red curve is maximizing the likelihood of observing the given data. Okay, so that's the maximum likelihood estimator in a picture. How does it work on paper? So here we have a bunch of observations, x1 through xn, all coming from a normal distribution with unknown mean. Okay, but we're given the standard deviation, sigma. In this case, the likelihood function is just the product of the normal distribution, but we evaluate it at x sub I, and we keep this unknown parameter mu. Okay. Now, by the properties of exponential, this amounts to summing the exponent, and we want to find what is the value of the parameter mu, that's the Greek letter here, okay, which represents the mean. What is that value that maximizes the likelihood? So it sounds like we should take a derivative, but a nifty little shortcut that we're going to do first is to take the log of the likelihood. So when we take the log of the likelihood, we're going to get this. Plugging in sigma equals 1 gives us this expression. So we take the derivative of the log of the likelihood. It's right here. And when I differentiate this one, first of all, this n over 2 times log of 2 pi, that's a constant, so it goes away. Now, for the second term, I need to take the exponent down. That gets rid of this 1/2. I multiply by the derivative of the inside. That's the derivative of minus mu, so that's minus 1. Cancels with a negative out in front. I get exactly this. Now, if I solve for the maximum likelihood estimator, that gives me this, which is just the sample mean. Okay, so that is a quick walkthrough on how to derive the maximum likelihood estimator, as well as what it represents in a picture. And what it represents is choosing the value of the parameter that maximizes the likelihood of observing the data for the distribution in question. Okay. Thank you very much.